this talk is gonna be very interesting because this talk is about gaming, right? Which we like. And this talk is about scheduling, which we have been working on. And this talk is about scxlavd, which is relatively new, so which is fun and relevant and new. That's the reason that this talk should be interesting to you. And I'm Chang Woo-min from the Igalia, and I'm the author of the scxlavd, which is one of the specialized scheduler for the gaming. Okay, so the goal of the talk is that introduce the scxlavd algorithm, and one of the reasons that I wanted to introduce the LAVD algorithm is that LAVD is a specialized scheduler, but its foundation is somehow very similar to the EEVDF. So I wanted to share my experience with you guys. So that's the thing. And LAVD stands for latency, criticality, aware virtual deadline, which is very mouthful. But as the name implies, its key emphasis is about how to boost the latency critical task to get the better user experience, especially in the gaming. That's the key things. And as I mentioned, the LAVD has some commonality with the EEVDF, but it also takes a little bit different approach and some tweaks with EEVDF in some other areas. And throughout this talk, I wanted to discuss about why and how LAVD take a different approaches. And they also wanted to discuss about some potential contribution back to the EEVDF from the high level, idea level, and some, if necessary, some code level. That's the thing that I'd like to discuss. Let me briefly introduce the LAVD first. LAVD is basically the overarching goal is the gaming scheduler. So since I'm young enough to be ambitious, so I wanted to make a best scheduler for the gaming, especially in the Linux. And if we break down to achieve the overarching goal, we can actually come up with 3 technical goals. One is that, especially in the gaming, the important thing is that they're reducing the tail latency. So people wanted to have a good throughput, good performance, but they do not want it to show the hiccup while they are playing the game. So the game community called that stuttering, or they have some metrics called 1%, low 1% frame per second. So they wanted to achieve the high low 1%, that's basically 99 percentile tail latency, and reduce the stuttering. That's the important thing for this particular scheduler. And the other one is that the many gaming devices are battery-backed device, so the power consumption is really important thing. And particularly, I have been one of the primary target device for this scheduler is the Steam Deck hardware, which is the battery-backed gaming console. So the minimizing the energy consumption is a very important topic to me. And another one is that the widely utilized heterogeneous process architecture is also an important topic. The reason is that many, for example, ARM SoCs has a big cores and little cores, and Intel also has the performance cores and efficiency cores. And also, many desktop gamers invest a lot of money to purchase the BP AMD processor, which has the multi-6x machines. So that's also the scope of the target of my scheduler wanted to somehow address well. And after thinking about this, if I'm able to achieve, my scheduler able to achieve all these 3 technical goals, that will be pretty nice desktop or laptop schedulers as well. So that's the kind of extended stretch goal, right? So the Linux gaming is something real. So there are especially in the Linux gaming, there are some Linux native games, but they are not the majority in the market. So the most important primary target is the Windows games, and they are run super smoothly on top of the Proton and Wine layer, which is the Windows emulation layer, and graphics, the API emulation layer. So the one thing which that implies is that the scheduler community have been discussed about their scheduler interface for a while, but unfortunately, our primary target is running the Windows games, unmodified Windows games. So it's a little bit unfeasible to describe latency hint from the application side.
Does Windows have any interface for latency?
Windows has some interesting API. So describe, oh, this is the task to generate audio and multimedia, but it is unclear that how many game engines and game applications actually use those Windows APIs. So if there are majority of the Windows game engines actually use those Windows API, then that could be also used to hint to make a scheduling decision, right? Does it answer your question?
Yeah.
Thank you. Okay, so the rest of the talk is roughly organized to address the three technical goals. And when we think about or talk about the gaming, the focused scheduler, right? The first thing that we need to think about is what's special or what's unique in the gaming itself, right? I have been good amount of the performance workload characterization study to understand what is unique things in the gaming. And the long story short, the most unique part in the gaming is that the games are super communication intensive workload. So for example, suppose that you are pressing a button on your game console, right? So from the pressing a button actually triggers the screen update and the audio generation, right? But in order to update the screen and play the sound, the many tasks, usually 10 to 20 tasks, are kind of interrelated very tightly together. So many tasks are tightly coupled and forming a chain of a task, right? Actually, this is the actual task graph that I actually collected from one of the real game. I remember that's the trace from the Cyberpunk 2077. And as you can see here, nodes are the task, and the edges are kind of communication between the two tasks. And the label on the wedges is how they are communicating. So as you can see here, most tasks are tightly coupled, and they are communicating through the ePOL, pipe, or the field text system calls, right?
Or anti-sync.
Yeah, sure.
So we'll be seeing anti-sync.
Yeah, so that's a good point. So in this particular trace collection, I didn't use the anti-sync patch, but of course the anti-sync comes into the picture. That anti-sync will become the major communication path here, right? So as you can see here, many tasks are tightly coupled to the wine server, right? So which basically means that if the wine server, scheduling of the wine server is delayed, right, then we screw, right? And the another thing which implies is that since in order to finish the one single high-level job, like pressing the button to update the screen, 10 to 15 tasks are interrelated. So if there is one of the tasks in the task chain are delayed, right, then we're gonna experience the cascading delay. So that actually causes the latency spike in the game, right? That's the thing. So that actually makes me think about how to determine the latency, how to determine the deadline in the LAVD scheduler, right? So as I mentioned, foundation of the LAVD is EEVDF, a little bit simplified version of the EEVDF-like algorithm. So the high-level ideas are basically the same. So how we advance the clock, those are roughly the same. So one of the reasons that I decided to adopt the EEVDF-like framework is that there are two reasons. One reason is that I studied the EEVDF before starting this project, and I found that, oh, this is a pretty nice framework because it can deal with the fairness treatment and latency requirement in a unified manner. That's important. That was important for me because I'm dealing with a latency critical task. And the other one is that if I piggyback on based on the EEVDF idea, then of course that our internal EEVDF implementation will improve, then I can steal some ideas. And also if I succeed in finding something useful, then I can contribute it back. So that's the reason that I choose the EEVDF as the foundation. But of course that in order to properly address the gaming specific properties, I actually made a little bit of the different decisions. So that's something that I'd like to explore. The first thing is that boosting the latency critical task, because that the gaming is mostly the latency critical application. So then the question is that how to determine the latency criticality of a task without relying on the program specified hint. That was the one of the most fundamental question to me. And actually I found there some hint from this graph, because all the texts are tightly coupled, right? So they are most of the texts are part of the task chain to complete the one job, right? So that was a big hint to me. So actually, in the LAVD scheduling algorithm, majorly we measure the two factors. One factor is that how frequently a task is blocked waiting for an event, right? That's the one thing. So actually, I measure the blocking frequency. So that's the one thing. The other thing is that how frequently does a task wake up the other task to notify the event. So the measuring these frequencies are not expensive, because it is just a matter of the when the task goes to sleep or becomes a wake up, then actually measure the time and do some kind of the moving average to sum up.
So the task waking up another task, that is O(n) squared in storage. So tracking how much one task wakes up any other task is O(n) squared in storage.
Yeah, but in order to very precisely calculate that requires a lot of computation overhead. But here at LAVD, we do not have such luxury, because some of the gaming consoles are pretty wimpy processors. So the only thing that we do is that how frequently I wake up the other task. So we do not care what are the other tasks. So just measure the frequency. And it seems to work okay, but later, if we, of course, need a more precise information, then that can be extended. But so far, it looks okay. Question you have? Okay. So yeah, so these two frequencies, the waking frequencies and blocking frequencies, the two major factors. And if the first frequency is high, that means that I'm a consumer in a task chain. If the second frequency is high, I'm a producer in the task chain. If both are high, I'm in the middle of the task chain, right? So that's the main thing. So if this is the major factor that we determine the latency criticality of the task, and the latency criticality is the high, then we should give a tighter deadline. So that's the reason that we wanted to boost the latency criticality.
Sorry, maybe this is a naive question. How do you detect when a task wakes up another task?
So basically, that's the matter of the problem that because that the wake up the one task to the another task, right? So that's when the task is waken up, right? Yeah. Then it actually checks the flags whether this is the wake up from the other task, right? Then that's the reason. That's the way that we actually know that this is the wake up from the other task. The short answer is that we use the scheduler flag.
Yeah, you check the current task.
Yeah,
that's the waker.
The waker.
But the wakey is the target.
Yeah, wakey is the target.
You also have to check whether it's an IRQ or not, right?
We do not check those things. We just check the.
Then how do you know if it was an IRQ that interrupted the task, and then that did the wake up, versus it's a task that actually did the wake? Those are two different.
So you're only looking at if interrupts are the same, or if you're not an interrupt handler. If you're an interrupt handler, you're.
But he said, I think you said you don't look at that.
Yeah, we don't look at that.
I said you should.
Yeah,
So you can skew your thing, because if you'll be at just one random task will start waking up. It just happens if a random task is running for a long time and a lot of interrupts go off that wake up, that task is going to be flagged as, oh, you wake up a lot of tasks.
Yeah, that might be the thing that I need to further fine tuning that things. But my observation so far is that if I actually take a look at the frequency distribution in the first and second one, is that these are hugely skewed. Right? Some tasks are very highly frequently blocking or waking up the other test, but the others are rarely do that. So yeah.
So wait, did I hear that you actually only look at when you wake up a task, you actually then monitor the task that got woke up and then put it in your little thing, or is it?
So we do not measure the correlation between what are the wakers or the wakies. So we just measure the frequencies because that's the cheapest to measure. Because we wanted to some information, but we do not want it to impose a huge overhead.
We do that something like that. There's some term called wakey clips that we maintain to capture essentially the same thing, but it's only used to determine whether we need to do a fine wake up or not right now. So we don't use it for determining the task criticality. So that information in some sense exists.
But also, like I said, another thing about using interrupts as your measurement too, usually that's like the start of a chain. So, like when you press the button, the interrupt that goes in. So that's the first thing that wakes up.
Yeah.
Well, likely. So actually, looking to see if it's interrupts or not, we'll say, oh, this is the start of a chain, so make it important.
Yeah, that might be the good. Yeah.
And check, so if I remember correctly, you do this check in the alt runnable holdback.
Yes.
Okay, and that's where you determine waker.
Yeah.
And wakey. So maybe even if it's in an interrupt, you end up maybe okay, the wakey is easy, but the waker maybe you end up flagging I don't know the interrupt or something that triggered the interrupt. I don't know.
Yeah.
I mean, there's an error, but
Yeah, there is an error, but
it's like
the distribution, actual statistical distribution is highly skewed. So even though there are some,
there's no ground on interrupts, I think.
yeah.
So it's
probably, if we run the same things on our,
it looks like they're running that flow in the background.
Yeah. And if you do,
You can't keep the pieces.
exactly.
How are you the basis to optimization?
the statistics is actually really the simple.
Can you repeat what John just said?
How long does it take to get to steady state where you have a sense you can make a decision?
It seems to be very quick, just a second or two, because that anyway, as I said, that the distributions are really skewed, right? So some tests are really generating a lot of the frequencies, right, in a short amount of time, and the other ones are rarely do that anyway. So I think that the few hundred seconds might be more than enough. I mean the millisecond.
But I would say interrupts are kind of important because if you're playing like a network game, you probably will get a lot of high. I mean, it's not random interrupts, it's not random wake-ups, but it's lets you know.
Give that some. I mean, but it's not the total effect, it's a network.
Right.
Well, because they can run latency, so they cannot saturate the network. Because they
I have a question. Sorry.
Yeah, sure.
How do you differentiate like between a chain versus just two tasks waking each other up, like ping pong?
Actually, we do not distinguish.
You don't distinguish.
Yeah, we do not distinguish. Yeah, we may require to distinguish those things, but so far it looks okay. So let's go with the simple way.
But it sounds like if you have a task that's woken up a lot and wakes up a lot, that means there's probably something in the chain.
Right.
Yeah.
If I remember correctly, you have like two frequencies. One is the waker frequency and the wakey frequencies.
Yes.
And then you have a formula that combines the two. So if you are a heavy waker, yes, you're prioritized. If you're a heavy wakey, you're prioritized. If you're both, it means that you're in the middle of the chain, so you're prioritized even more.
Right.
And so I think that's why it's working. Because
And how quickly does this decay? This evaluation. The evaluation, once you figure out that something's in a chain frequently, is there some time period over which that will decay that you'll stop prioritizing?
Yeah. Actually, the what I may do is that doing some exponential weighted moving average. So the things are naturally decayed. Yeah. Formula is not very complicated. Yeah. Okay, so that's the one thing. And the other thing is that the one thing that I actually found is that the strictly enforcing the illegibility is not good, especially for the game. The reason is that for example, a critical test like wine server, right? So most of the distros, wine servers are just have a nice zero value. So that might be wrong, but anyway, that's the reality. And anyway, somehow embrace it. So those critical tasks may consume the more CPU cycles than it's allowed. But if we just punish such tasks for due to the ineligibility, that actually cause the text change stuff momentarily. That actually cause the hiccup in the frame. So that's the thing.
The program scripts themselves, they start wine at -10 or something.
Yeah, actually some do, but some other distros doesn't do. But yeah,
And as long as you use Proton, it will. And even Lutris and Bottles and all the other, they're able to program GD. So you're always run the program script. So wine will always be -20. It's just if you run the distro native wine, which you shouldn't do if you care about the game. They might do different.
Yeah.
Basically, for gaming, assume wine is high priority.
Yeah, and also besides the wine, most of the games create a bunch of the task pool, the thread pool, and some of the thread in these task pools do more jobs, right? And because they are in the middle of the chain, so we also need to give them more the time slices, even though they have all nice zero values. So that's the thing that I'd like to say. But the one thing that I also observe is that completely ignoring the illegibility and fairness is also not a good idea, because that some of those tasks can monopolize the CPU and also serves the other tasks. So somehow we need to have some balance both. Somehow loosen the illegibility enforcement, but we need some level of the illegibility, right?
So, question for you: in these task chains, like just talking about a thread that is doing most of the work, how do you know the relationship between the waker and the wakey? Is there like some sort of a wait on or something like that?
So actually, we do not track the.
But the user space itself, the program itself, does it know that it's waiting on something to happen on the next thread?
So from the user thread perspective, right? So I think they are just simply using the system library, or if they are making a thread pool, they are implementing their own software pipelining through the field tag or the pthread API.
So I mean, isn't this like essentially proxy execution? The job. Isn't this essentially proxy execution in the sense that you're passing on the property is, I need to make progress, and I'm waiting on this other thread to make progress. Maybe it should run in my place till I can make progress.
I don't know if I see the parallel quite so clearly, but that sounds like proxy execution. I just don't know if I can link that to it. It's in the presentation. Yeah.
No, I mean, instead of losing eligibility, it's essentially now saying I am eligible to run, but I cannot make progress because X thread has to run, which is not eligible to run.
In my point of view, in some sense, that the proxy execution and this LAVD algorithm consider the relationship between two or more tasks. So there are some.
That's kind of what I was asking.
Yeah.
Using something like thread muplexes or I mean, we don't know what the user space is using, but if it's using any of these constructs, that can then be educated.
So this relation also doesn't strictly rely on the blocking. So proxy execution relies on the wakey going to sleep, whereas this does not. But it has similarities.
Yeah.
Also, it can be more than one task directly without the same time. So then you have to reason how to make donate to multiple tasks.
Yeah, no, that's the question, right? So what's the relationship?
Here, I'm not sure exactly how to see who's the donor. Good question.
The donor is the thread that is waiting for the.
That's right. Well, I guess in this particular case, it might be the wine server. It's at least from the graph that you showed.
Yeah, this one, but there are other ones
There
which
are
are in the
ones,
middle of
yeah.
the chain that will
It's not that easy.
have a shorter deadline when actually making a deadline decision.
Yeah.
But it does not necessarily for the task who boost it, doesn't necessarily to have become a rock holder in this particular case. So even though in some sense there's a little bit, this one is a little bit loose notion because the legalist of having a rock or not, if I'm in the middle of the chain and my one is very frequently being a middle of the task chain, I'm going to be boosted, right? So that's the one thing. And the other one is that I also found that besides this, that there are some hints that we can actually get leverage from the implementations. For example, the synchronous wake up, which is the one thing that we use as some contextual clue. For example, similar to the proxy execution, the rock holder, for example, especially I'm actually tracking whether a task holding a field text rock or not. If the text is the field text rock, then give a little bit of favor in determining the deadline. And then also the affinitized task and kernel task, those are the tasks having really typically the latency critical and having some constraint in the placement of the CPU. So giving a little bit more favor those one. And many existing applications still using the nice to describe, oh, I'm an important latency critical task. So a little bit of hint, I use the non-nice task, a little bit of the flavor. That's also the pretty useful idea. So that's what I found. So put this all three things together. So this is the equation for determining the deadline. Of course, the current clock plus the text average runtime, which basically means that we're gonna favor the short running task because anyway, long running tasks, even though there are some scheduling delay, that wouldn't affect a lot. So, and then if task is the latency critical, right? Then we're gonna actually want it to have the shorter deadline. And latency critical is basically wake up frequency and blocking frequency plus the number of contextual clues, right? And also similar to the illegibility, we actually measure how much time is overspent by the task, right? And that actually calculate by the ratio. And if the task spend more time than I was allowed, then it actually get penalized in determining the latency criticality thing. So determining the deadline. So that's basically the idea. Any questions so far?
So, can you go back to the previous slide? So you mentioned how much time we exceed compared to the runtime that was allocated?
Yes. So actually I prepared some demo because this is about gaming, so we should see some gaming things. Yeah. So as you can see here, this is the frame time graph, and this is the frame per second. So the Space Marine 2 works fine with the EEVDF without any background job. So the screen is smooth, right? And there is a little bit of the hiccups in the frame time, but that's not a big deal. So actually, I ran this one on the Steam Deck hardware, which is the AMD processor having 4 physical cores and 8 logical cores.
In gamer parlance, a potato. In gamer parlance, a potato.
And then let's run the background job, which is emulating because the gamer try to run all other kinds of things while they are playing games. For example, having a Discord call or the recording the game scenario, right? As you can see is that CPU now that becomes 100% and the frame time fluctuates a lot. And the frame per second drops from the 60 frames per second to 25 frames per second, right? That's kind of expected because there are CPU working tasks, and in order to enforce some fairness, right? So game also should be equally penalized. So, and then I'm going to run the LAVD scheduler. Yeah, so even though there is no move, right, the frame time fluctuates a lot. Yeah, I think this guy is taking a rest. Yeah, let's launch the LAVD scheduler, and the same background job is still running. The launching BPF schedule is just nothing but just a launching a thing, right? The user sudo permission. So as you can see here, the frame time becomes kind of stabilized. And frame per second is not 60 frames per second. Of course, there are background job, but which is the 45-ish frames per second, which is still playable. So the thing is that the gaming tests are frequently in the middle of the chain. I just boosted, so that's the thing. Yeah, I think let's skip the second one.
Okay.
So there is another video in the Elden Ring, but if you wanted to see the Elden Ring video, basically the same thing, right? So you can download from the Google Drive and take a look. Yeah. So one thing, so actually I didn't have a much. Okay. So one thing that I actually, even though I didn't test the LAVD besides the gaming workload, but at the high level, creating a software pipelining and creating a test chain is a pretty common software development practice in many domains, right? So probably it might be worth to consider such latency criticality metric to the EEVDF or our mainline scheduler. So that's the one thing that I'd like to hear the opinions. Maybe I might ask the too hard question to Peter.
So, yes, it is a hard question. I think the graph inference is definitely something that we can look at. Grading fairness like you do, maybe not.
Yeah, I agree.
I mean, if you want your game to get all the cycles, I mean, just nice to think. That's what they're for. Conversely, nice the CPU so. So yeah, I think we can look at some of these things.
Just to add what Peter said, I'm just curious how much of a difference it would make if you ran the same test but nice background test.
I didn't actually do that, but Angela did
something. So the problem is that yes, you get a better average FPS, but the tail latency, you still see the spikes because you get more time spikes, but you're still affected by the noise that is
right.
So it was the eligibility that affects you? Is that the issue? Is the disabling of the eligibility or the overriding of eligibility? Is that what's?
So in this experiment, actually I looked through the eligibility in first one, as I explained.
Yeah.
So anything else you are asking?
So yeah, I mean, your interface will happen because of that, right? Because you may not be immediately eligible to run.
Right. That's the point I'm saying. What nice help if you lose your eligibility. Still, is that what causes displaying the eligibility back?
Yeah, I think if you disable eligibility in EEVDF, you may get a similar.
Because that's exactly what from our test. When we just disabled eligibility, things, all the just things work. But then again, when you do that, you have things that could then be. It's no longer a fair scheduler, but you know, honestly, a desktop environment,
who cares?
You don't want a fair scheduler.
I agree.
Yeah, in some sense I agree because the desktop owner owns the desktop, right?
Yeah, this is basically what I'm doing more or less in BPF. BPF is pretty much EEVDF with a slightly different deadline, but you know that's just details. And I don't have the eligibility concept. I mean, I'm fine to break the fairness constraint just to get better performance for that particular use case.
Because ideally, you want that to be unfair to everyone else.
Yes, exactly.
That's perfect.
Then fairness you can get in nice priority. Did you try? I mean, what you were showing there for me, it's really like, so you're monitoring the number of
waker-wakee position, and based on that, you are modifying the nice priority as well to get more time sharing, and probably modifying the slides to be scheduled first. Did you try something like that? I mean, that's really what my understanding of what you're doing. You have something to monitor if you're waker-wakee, and then based on that, you try to compute the CPU boundaries that you would like to provide to one task, which is the nice priority. And then you would like this task to be scheduled first, which is typically right now what we have with the scale slice. Shorter scale slice with INI, so we have more, we will run more often in priority.
So at least based on my experience, that having an earlier deadline is the more important than having a longer time slice, because most of these tests are really run very short, so they are actually going to sleep.
But that's the point. I mean, by default, everybody has the same slice duration, so it's clearly a random choice which one should run first. If you decrease the slice of your latencies on this task because they should be short running tasks, they should run first and take it. They should pre-out the long task and run first. You can increase the niceness to make sure that even if it starts to run longer, you will get more time in this short duration. But that's really look like that from what I have seen.
So, if I understand correctly, that sounds like another way to boosting having a shorter deadline in the EEVDF framework, right? I agree.
And also disable the run to parity. If you play with the run to parity might be an issue for you. You will be forced to wait.
Any other question? Okay, then.
One question: how dynamic or static are first joins?
They said they were fairly static.
How dynamic or static for what?
The software pipelines, the first joins.
I think I should say that is pretty dynamic. The reason is that in my observation, the game engines and games are creating a gigantic, let's say, 30, 40 thread pool and dynamically assign the job, right? And then once the job is assigned, then actually it seems to work for the same job forever. So it is really hard to...
So basically you have a thread pool.
Yes, every single game engines have creating a thread pool.
And they pick a random one.
Right.
Okay.
Okay, so I think that's the most important thing that I'd like to discuss. And second one is that how to minimize the power consumption. 5 minutes? Okay, so let me quickly go over the second one. So because I think the first one is the most important thing that I'd like to share. Second one is that in some sense, the discussion is about somehow related to the EAS algorithm, but this is more kind of based on the observation in the gaming uses, right? So people tends to place the AAA game, which is the really heavily multi-threaded and consumes a lot of CPU cycles. But on the other hand, they also like to play the old casual games. But these old casual games are much less multi-threaded. They just have 2 threads or 3 threads they created, and then consumes much less CPU cycles. And even though, since that's old, even though they just have a 20 or 30% of CPU cycle, CPU utilizations, they can easily achieve 90 frames per second, right? So that's not a big deal. So what I'm trying to do is that especially how to capture and minimize the power consumption in the second case, right? Anyway, in the first case, the gamer's goal is that wanting to achieve the maximum performance, right? So especially in the second case, what I'm trying to do is that especially the system is underutilized, like the second case, that instead of spreading the task to all of the older CPUs, let's restrict the number of CPU which is actively being used, right? So that basically makes the rest of the CPUs stay on a deeper idle state in a longer period of time, so we can actually save the energy. So that's basically the idea. But at the same time, we do not want it to utilize too small number of CPUs, because if we just utilize too small number of CPUs, that basically means that the task will be fired up for the execution, and the latency will become higher. And another important thing is that if the CPU utilization becomes too high, then that CPU could be turbo boosted unnecessarily. That consumes a lot of CPU power. So that's something that we avoid. So practically, what I found is that 50% of the CPU utilization for the actively using CPU seems to be okay without causing the scheduling delay and the turbo frequency triggering. So that's the thing. And then the LAVD has a feature called core compaction. Basically, the idea is that periodically using the BPF timer and measure the system-wide load, and then determine the number of CPU that I'm going to actively use for the duration of the time, and then make a best effort to place all the tasks only to those group of the CPUs, so that the rest of the CPUs stay in their deep idle state for the longer period of time. That's the key idea. So that's the third part that I'm going to discuss about. But in this initial version of this one, the core compaction, we didn't thought about the topology, because that the initial target hardware has just AMD 4 physical core, 8 logical core one. So, but later I'm actually extending this idea to the topology as well, considering the big and little cores and the multi-RLC machines. Yeah, that's something ongoing.
I have a question. When you say 50% load, what about frequency switching? Is all disabled in this, or you also consider?
So here in this case, that we are still relying on the underlying frequency governor things. So, for example, if the user using the Intel P state or AMD P state driver, right? So the frequency will be determined by those drivers. So this is a kind of the best effort approach from the scheduler side. Of course, that the LAVD has the schedule implementation as well, but the main thing is that relying on the underlying or the schedule frequency governor.
You're keeping active the schedule and the frequency switching is being active. It's not disabled in this.
Yeah.
Because the question is, if you have any decision to take, like, is it better anyway? Two CPUs at 50% at full speed, or four CPUs, still 50% load, but half of the speed or whatever. You know what I mean?
How do you measure utilization? It is not PELT, right?
Oh, actually, I may rely on the PELT, but my current implementation is that my own BPF level implementation. So basically, things are because that the SCADX has a hook. So actually, before tasks are running, it calls a running callback. Before stopping, it calls the stopping callback. It simply just measures that
okay, so it's a time.
Yeah, the time measure. Of course, it does not consider the CPU clock frequency. So yeah.
Yeah, so my point was that it looks like you're trying to control something, but underneath there's another independent mechanism that tries to screw up your load percentage.
Yeah, actually that's true.
Right, so if you don't do something jointly...
but the thing is, like, correct me if I'm wrong, you also have like default ways to like max out the CPU free cover, no? If you don't enable the CPU frequency integration, right? So it would just max out the frequency. Then everything is like going full speed, and that's if you also enable CPU frequency integration, which is optional, then yes, you have this, you have two moving parts.
Yeah, sure.
Yeah.
So that is not true. The reason why is because there are
Yeah, sure. The frequency is also implicitly scaled, right?
For modern CPUs, that may be true, but for some older ones, it's like if you the turbo states are not sustainable enough.
Yeah, sure.
Otherwise,
So for new processors, I think that this doesn't matter that much because they can sustain turbo for longer, but then for older, maybe not.
we should see on the Steam Deck, like what's the effect, the impact on the Steam Deck.
Yeah, so
It's Zen 2 right now.
It's I don't know, it's an AMD. What's the Steam?
AMD processor.
Zen 2.
But that's
Excuse me?
Zen 2.
Yeah, Gen 2. This is Gen 2. Currently Gen 2. So one of the things is that actually run is the Tomb Raider game, which is the pretty old game. And regardless of whatever schedule you're using, so we can actually easily achieve the 9 frames per second. But using the core compaction, the LAVD actually draws a little bit less the energies. So that's the thing that I'd like to see. And currently what I'm doing is that extending the core compaction idea, as you mentioned, they're considering the big little architectures and the multi-head architectures. So that's all I have. So any other questions?
So how do you decide, like, so I guess right now you're using the number of CPUs and the amount of time that makes it look like it runs half of the time. So if it's running more than half of the time, you just bump up the number of CPUs?
Because they actually will be adjusted in the next cycle.
Okay.
For example, if the CPU utilization is actually larger than the 50%, then we're going to assign more CPUs to make the CPU utilization below the 50%.
Yeah, but it might be higher than 50% because the frequency is too low, but you don't know what the frequency is.
Actually, we do not explicitly control. We do control the frequencies because there is a schedule implementation in the LAVD, but if users do not use the schedule util, but they rely on the other frequencies and CPU governors.
But on Intel, they have HWT.
Yeah, but this might be something that you can squirrel away in the energy of the curves. That ramping a CPU over 70%, say, might be more expensive than starting a new core, and then I think EAS will do something like this.
Yeah, so this is very similar what I do in the second EAS support implementation. So this is like up to 40% of utilization if you just use the same CPU until it gets over 40%, and then it will go to the other.
So that's the async compaction? Is that async compaction or something else?
It's EAS, so it's like in the energy models, so it's like in this case, but
Okay, I think we are done.
Okay.
Thank you.